that helps, sure.
Hello again. It's like first time we've seen each other in a week, you know?
Yeah.
Thanks to all this SOE stuff.
Say something a little bit more substantial yesterday.
Well, I can tell you it's exactly what he said at lunch.
Same thing?
Yeah, I mean, the way it was presented was different. One was over, you know, over food. The other was standing up in front of an audience. But it was full of anecdotes and
The defense.
we see a lot of this guy now.
Yeah.
No money. I'm
Becoming a true winner for that.
leaving. I keep saying that.
Well, we already graduated. We did all we could.
That's right. You kicked me out and I came back.
Yeah. How's your wife feeling now today?
A little better.
So I have a question for you regarding Princeton. Community Park at Johnson Park. Which one is it? Yeah, we might be moving, yes. I'm tired of driving across Princeton to drop Mira off at school. She goes to Stewart now. And, you know, if I miss it by 5 minutes, I'm stuck in traffic for 20 minutes, so. Now, a lot of other reasons. You have to know why. Which one? Part of documents. One of them is not so good. Forget which one. Community Park. Why is that one not so good?
It's right next to it. Some of the defense slopes.
I thought it was the Johnson Park, and that was not the one.
Johnson Park is
the south side.
No. This is real.
Or maybe
It's a very different environment. I think.
or maybe the word park is what's confusing. All right.
This will have a process or use.
I can then understand that
The
rationale.
environment where the book for gets all that school.
No, I don't know.
All right. But it's not. All right.
Yeah, but
Some people like it.
No, this is comprehensive. There's a rationale why one of those
Community
was.
park is a
That's like a downtown area, right?
Yeah, it's not a downtown.
Yes, so it's near the swimming pool, right? It's the swimming pool one, all right.
I know.
And just 1-2 blocks south.
It's just
It's still a fine street.
also just maybe
Probably somewhat exaggerated.
And they all have an October 1st cutoff.
no, it's the sign up there.
Or it's October 4th. That's the problem.
Somebody has the link accepted.
We're not nearly
Well,
that secure.
he would now be the oldest. He would have to take kindergarten again. And he's actually, he's in kindergarten now, and he's the youngest in kindergarten, and they say he's. Really? All right.
At least I tried it, I've seen it.
All right, so maybe that's an option. All right, well, anyway, thank you. I'll probably,
For some kids, it's better to feel it. Normally I would start on it, but
yeah, the school exact same. expect for 5? All right, you put it nicely, a boy. He does have his own issues. He hurt himself 3 times yesterday. Great things that are just a boy's job.
So when did you guys decide on Stuart?
I got really mad at South Brunswick. They did some things that I definitely didn't approve of. And in fact, I asked them not to do, and they still did. And that, and we don't really fit. There was some testing they did for gifted and talented. This is one of the examples testing. I don't know. Basically to pull your kid out and advance them up a level. All right, but then bring them back to the normal class. That leads to segregation issues that I don't approve of. And they did it 1 year, and I said, please don't do it again. And they did it another year. And on top of all that, they sent the results home in years back. And she didn't pass home. And I had my only daughter for 2 hours, and I had to deal with smart enough to figure out the test wasn't fair. You're in first grade here, being asked to solve division problems. You know, what do you do? All right, you don't know how to do it. So, and then I'll tell you other reasons that are much more.
Are you okay? See you again. See you again.
I know that long and the no, I'm all set.
Okay, so are we missing anyone now or we good?
No, I think we can start.
Okay, so welcome everybody. We have the public PhD thesis defense for Francesco, who has been working with me for the last 4 or 5 years. I don't need to introduce Francisco to you, but I would just say he's done a lot of work here. He's been one of the systems PhDs over here who has done lots of implementation for each idea he has pursued. So he'll be giving his talk and you can get an idea of the details. Go ahead.
Thank you.
If you could target about 1 hour, and if it goes slightly over, that's okay.
Okay, I'll try to stay within the time limit. And thank you for the introduction. I'm happy to have you all here. As I was saying the other day to a friend of mine, I'm not sure that 100% of people in this lab know exactly what I've been doing over these 4 years, so I'm happy that you'll get one last chance to see what I've been going through. And I'll be talking a bit about the work we've done on trying to create new abstractions for the future internet. So, after many years of constant evolution, the internet has approached an historic inflection point where mobile platforms, applications, and services are taking over the classic fixed host server communication paradigm that characterized the internet since its inception. Moreover, this evolving process in these last few years has been enabled by an increasing reliance on new fundamental technologies and approaches that have enabled these new services to start growing in importance and populate the internet. But while these technologies are very important, and you'll see this throughout the entirety of my work, these services are expanding their requirements. They're increasing the type of work that the network does to a system, And we've been working throughout this work and trying to find new solutions to support these network services. But instead of focusing on small problems and tackle them one by one, we try to somewhat approach the problem from a more top-down perspective. So first, defining and identifying the set of most common scenarios that are characterizing networks today, and mobility, content retrieval, Internet of Things are some examples of this. Trying to identify what key abstractions could help enhance the utilization and the usability of these use cases by providing ways within the network to, say, support content retrieval or group-based communications that could enhance these use cases. And finally, design and implement and test these new protocols that are aimed at supporting these services. So before jumping into the content of the thesis, I will span across different layers of the network architecture. But this should give you the idea of how I've been trying throughout my work to always focus and try to identify the high-level aspects that were required for each of these components that I've been working on, and step by step get to the end of this thesis. And I should not forget mentioning that everything I've done has always had a lot of focus on designing and actually implementing the aspects that I've been working on and deploying them on different aspects. So, first things first. You have noticed that the title of my thesis talks about named objects and how they could be used for the future internet. But name-based architecture are not something completely new. They have been proposed over the last decade or more, and they've actually gained a lot of traction within the research community. So it's important to kind of address what other architectures have been proposed. And while I won't go into the details, there have been different attempts at defining what's the fundamental abstraction that defines communication networks. One example is content-centered networking, where the research community departed from the classical IP aggregation of names and addresses, moving toward name-based content retrieval. Another different approach is the one that will follow throughout this work, where names and addresses are connected through the use of a name resolution service. But I'll leave that for later. The most important thing I want to highlight is that within all these architectures, there is a commonality, which is the way that network objects are referred to. Whereas instead of referring to network objects as their location, their IP address, we refer to them by name. And we can get ways of actually interacting with them in more advanced scenarios instead of the classical link-to-link communication patterns. And any cast and multicast are examples of these. But before actually working on the architecture that I've been developing over the last few years, we started focusing first on trying to define a set of core abstractions that we believe that will be fundamental in evolving and in providing solutions for the services that I was mentioning before. And these abstractions are in particularly 5. First, the name-based communications. I mentioned that in the previous slide. Name-based architectures can help with different type of communication patterns, in particular, for example, mobility, where unbinding the name of the objects you are communicating to can help support basic mobility services within the network. But we believe that this should not be done as only a receiver-initiated operation, as in other architecture, but it should also be allowed to be a sender-initiated architecture. Second, these names should enable communications with any type of network object, not limiting to devices or content, but span across different type of network elements. And services are another example. Context has been a growing important one. Third, there should be a way to address multi-point groups with different type of delivery services. Multicast and Anycast are examples of these. Moreover, multi-homing is an important way of exploiting the type of resources that are available in all the devices we have today. Then we have the last two, which are trusted identities. The IP network was not intended to have built-in security in its protocol stack, and these should be addressed in any type of abstraction that is provided by the network. Finally, the possibility of referring to network resources that are more advanced than simply the communication channels that are available. And so, for example, being able to exploit resources like caches or computing power that are available within the network. So, while this sounds like a lot of different abstractions that are supported, we understood that there is one. We started understanding and working on the fact that there is one important abstraction that can single-handedly support all the different, all the 5 requirements that I expressed before, and this is called named object. So, to give you a brief idea of what a named object is a way to separate names and addresses to provide a new type of communication. So, first of all, a name defines what we're talking about. So, it can be a device, it can be a content, it can be a multitude of endpoints, say a collection of sensors. So we want to have a way to refer to these different type of objects. And this is the name. Then we are interested to know where these names are, so that we can have ways, the network can have ways to communicate with them. And finally, once this is defined, we want to give the network a way to know how it should be, how it should deliver the data to these named objects. A representation of this concept is the MobilityFirst network architecture. And I'll highlight the core aspects of the architecture. So first, we find the new narrow waist of the network architecture, which is defined by a name layer where names are flat globally unique identifiers that we call GUIDs that are available for network attached objects and are resolved through a globally available logically distributed name resolution service, which provides bindings from the names to their location. This separation of names and addresses is supported within the network by an hybrid routing scheme, where network headers carry both the names of the entities that are participating in the communication and the network addresses. But network addresses can be dynamically resolved by the network fabric through the name resolution service. So if a message is sent, a router can retrieve where the network object is, set it up, and set the path up and deliver the data to the destination. Well, this is supported by a name-based API, which provides ways of accessing all the different type of communications that are available. I forgot to mention, sorry. The how that I was talking about in the named object is actually supported by the use of a flag service identifier that can be placed conveniently in the network header to provide ways for the network to know what type of data is being delivered. Then there is a name-based API that provides ways for accessing the different type of services. In this case, I'm giving an example of how to deliver data to multiple entities that belong to the same group, whereas the network fabric can retrieve multiple network addresses and then deliver the data to the destination. And finally, it supports advanced computing services that are available within the network. So the first step of my work was trying to define a new network API that could exploit all these concepts, all these resources that are available in the network. And these closely follow the patterns of the abstractions that I've just defined. First of all, it's a name-based API. It uses GIDs, which can double as public keys and private keys to provide the trusted identity services, the security aspects. And it uses names to communicate. It provides addressability for all type of network principles. So it not only allows for classical one-to-one communications, one-to-many communications on a message base, but it also allows for content and service operations, where you can retrieve a content by explicitly requesting to a GET operation or invoke a service through an exit operation. And it allows the management of network presence within the network. So announcement of the bindings from names to the network addresses they belong to. And finally, it allows, through a set of dynamic parameters, to invoke different type of delivery services, so multi-point addressability is an example, or to invoke the in-network storage that is available within the network. So after defining this API, we started looking at the first very few experiments that I've done in Orbit were aimed at trying to find use cases of how this API could be exploited to showcase its merits. So the first one that we came out with was trying to look at how content retrieval could be simplified using this API. So in this simple example, we have a client that wants to retrieve a content that is duplicated at multiple locations, which have different connection characteristics from the client. Obviously, the client is not interested in knowing from where the content is retrieved. It just wants to optimally be delivered to retrieve it. So he's requesting the content, and he's requesting by using the Anycast service. The network has to solve the problem. So the amount of code that is required to actually perform this operation is very limited, because we don't need to know where the contents are. We don't need to take care of anything of those aspects. So the client starts retrieving the content. Everything is going perfectly fine. It's achieving the maximum available throughput. But then there is a failure in the network. There is some time at which this failure is affecting the communication, but then the network can realize that this failure happened and start retrieving the content from the other location by remapping using the network resolution service. And all this process is handled within the network. The client doesn't need to perform any operation. And this concludes the first part of this talk, where I presented the new service abstractions that we came up with. And I started talking a bit about all the work that I've done in terms of prototyping these architectures components and getting some experimental results to evaluate them. But while these abstractions are potentially very powerful, they can provide access to a lot of different services, well, the network does need to provide support for these services. It's not as everything comes for free. So I started working on a different set of problems to try to address how these API could interact with the network to actually get the best possible out of it and exploiting the type of services. And I focus on three important pieces. How to address multicast services, how to address in-network computing resources, and how to define context services within the network. So the first one, I've been working with Tracy on this, and we actually defined a full design for this solution, and through simulation we got to some results, some control overhead results. While the other two are more design guidelines and experimental evaluation. This means that we design the components and deploy them on experimental frameworks. And I'll talk about this, but sadly due to timing, the context service won't be part of this talk. So first things first, multicast. So we came up with a named object multicast solution. What does that mean? That we use named objects to enhance and simplify the deployment of multicast services. So multicast has been a very popular topic in the research community, but also somewhat of an unresolved problem. There is no real implementation of multicast within the network available today. So how do we support multicast through named objects? There are two defining designs that are particular of our solution. First, we use named objects to provide participation of endpoints within to define participation of endpoints within the network. So we define a unique name that identifies the multicast group management name ID. And all participating destinations can have themselves as a mapping given their name, so that we have a single binding between the multicast group name and all the people participating in this communication. This information can be retrieved by the service of the multicast group to actually build the tree. And the tree is actually set up in such a way that this information is made available still through the name resolution service. And the representation of this tree is actually a recursive definition of it. So we have the multicast name of the data path multicast name that maps to the first router that defines the tree. Then the name defining the tree is mapped to the next two steps in the tree, and so on and so forth until we get to the destinations. These allow basically the participating routers to just need to conveniently tunnel using the names that they belong to, tunnel data from to traverse the tree, reaching the destinations. So this is like, in our opinion, a neat and clean solution for multicast. And it has particular importance because it simplifies a lot inter-domain management of multicast delivery services. But obviously we had to prove this. So we analyzed the control plane overhead and compared it to PNSM, which is coupled with the MSDP, which are the standards for deploying multicast services in the internet. And we saw that these the amount of control overhead, while in the classical scenario of IP-based multicast explodes, once the size of the multicast tree increases, our solution actually is a lot more under control. And this is because the IP-based solutions are required to actually flood the creation of new trees, and they need to return back join messages from the new participating host all the way to the source to maintain this tree. While in our case, we can conveniently interact with the name resolution service to provide this information to the participating hosts. And there is no need for specific control overhead in terms of coordinating different domains and different networks across the internet. Another fundamental aspect where our solution helps improving the control overhead is within in mobility scenarios. So changing mobility of participating nodes within the multicast group in IP networks actually causes the tree to have to be recomputed, and this can be really costly, especially if it has to happen multiple times. In our case, this is not, and all the data that is flowing through the multicast tree while this tree computation is happening is lost. There's no way to recover. In our case, these three computations can be delayed and performed only at convenient times because we can handle mobility in a much cleaner way. And this is because if we take this example, when host D1 moves from one network to the other, when data that is destined for the participating clients in network 14 is received by the gateway router, the gateway router can see that those hosts are not available there anymore, and can query the name resolution service for the new location of where the hosts moved, and generate and basically create repair traffic to actually deliver this data. So no data is lost, and we can see from the simulations that we run in NS3 that the throughput is maintained throughout time when in the IP case is falling down.
Francesco.
Sure.
So in this case, right, what I understood was that there are two things happening here. One of them is the use of the named object, and the second thing is the use of, instead of doing a fully distributed multicast tree setup, you have moved that out to the GNRS service.
So I didn't go too much in detail into that aspect, but the idea is that we use a service gateway close to the source of the multicast tree to actually build the tree and notify the participating nodes that they need to, they will be participating in this multicast tree.
Okay.
Obviously the tree is inserted into the name resolution service so they can query as needed.
Right.
But the path is set up for them.
Right.
So whenever, this tree can be periodically recomputed by the service gateway and redistributed. But as the information is also available globally in the distributed service, it can be dynamically retrieved to solve issues like mobility and avoid data failure. And these can also be conveniently used to create dynamic multicast groups. So imagine that you want to create a group that needs only to live for a short amount of time. You don't actually need to set it up completely, as is the case for IP multicast. You can just use dynamic resolution from the name resolution service.
So my question is that, suppose I didn't do the naming part. My question is, how much of your gain is coming from the fact that you have this third-party service that anybody can query in case they run into issues, versus, I know that the GNRS depends upon the named object, so it is all tied in there, but what if I just had IP multicast and I separated it such that anybody can query this third-party service when there is mobility, versus the full architecture that you're proposing with
Well, there is one small aspect that you're forgetting there,
right,
which is that a multicast address is a unique address for all participating nodes.
right.
So you can't really do what you're saying because you will have to rebuild the way that IP multicast is working. So basically if you say, okay, I'm actually using unicast and I'm building this infrastructure as an overlay solution on top of the existing IP where participating nodes are using unicast to receive data and you're tunneling through.
No,
I agree with you, but that's actually exactly our solution, but implemented as an overlay solution, right?
Right, right. No, what I
So-
was saying was that the IP address of the name is just a pointer, right, in the case of multicast. So if I maintain a tree as a third-party service and that tree can keep gets updated, does it really matter whether I use a name or an IP multicast address?
Well, it does in the sense that the IP multicast address, I mean, you're kind of, the IP multicast address, either you use that as the definition of your tree, so you need to first set up the tree.
Right.
And so we're going back to the other point.
Right.
If you're saying, okay, I use just that as a pointer and then I use unique IP addresses, then yes, but you're basically just using the same concept and moving it to IP.
Right, right.
So yeah, it works. This is not strictly binded to having MobilityFirst. It's like the idea of having the named objects abstraction to implement that.
Right.
So sure, you could implement it as something on top of IP.
Okay.
So next step was trying to address what type of concept could be used for network compute services to provide extensibility and upgrade options in the data plane by exploiting all the resources that are more and more commonly available within the network. But there were three key design components that we needed to define, and we actually allow for some flexibility in the sense that we identify two possible solutions for all the three key elements, but these three key elements are fundamental in our opinion. The first part is having a way to address these services. So one can say, okay, I have a data packet that is flowing, there is an option for me to address this in network services, whether some conditions are met, but I need to understand how I know whether this service should be invoked. And we identify two potential options. One is direct addressability within the network packet itself, which is what is represented here. You use some extension headers in the network header to identify everything. And you can actually provide arguments that carry more information about the packet that is being delivered. Or alternatively, use transparent invocation. And this is based on packet header signatures, and it's similar to today's. Today's approach is with the advantage that you are actually invoking, you actually know a lot more about the type of data that is traversing your network by use of names. The second part is a more of a technological issue, which is, okay, do we use more close hardware integration with the network fabric, maybe embedded in the network fabric itself, or collocated compute resources like cloudlets are an example of this. Well, in our solution, this doesn't really affect the design in the sense that both are supported and available because we're really just addressing a service by name. And finally, finding a way to allow the network to select the best possible solution of the service, because these services might be replicated across multiple locations, and we identify two possible ways of doing this. One, by using native MobilityFirst tunneling through GNRS management, and there's an example of this, but this remembers a bit the solution employed in the Multicast previously presented, or using service ID network engineering to simply predetermine possible locations in the network itself, but this is more costly, and the name resolution based one is more flexible and dynamic. So, as I said, we actually implemented these and deployed a use case example, and this use case was in network transcoding. So imagine today's video feeds, video streaming, they pretty much, most of them use a technology which is called Dash, which basically is used to represent a video as a set of chunks that are retrieved from a content server. The clients, in order to optimize their transmission, especially if they are mobile, but also for wired networks, this applies as they have to handle congestion in the network. Network clients can select different type of resolutions at which each piece of video is available for them. But this is kind of inconvenient because it's all based on the video client to predicting what the network conditions will be. So what we try to look at is, okay, maybe if we deploy an in-network transcoder that can conveniently query wireless resources to understand what's the current condition of the client and optimize the data rate and the video rate at which each piece of video is delivered, then maybe we can do a better job. And this is what we did. We use our in-network framework to deploy. The forwarding logic actually is enabled by to query the wireless network resources for the condition and determine whether data chunk should be forwarded to the in-network transcoder or not. I won't talk too much about the results because I'll come back to them in the last part of this talk.
Francesco,
Sure.
generally there's also a trend of moving just the content service closer to the edge. when you compare the transcoding approach with that approach, when would you use them?
Sure. Actually, that's something that was discussed about, in the sense that this solution kind of assumes that whatever happens between the content server and the edge network where you provide the transcoding is fine, and how much data you can send the best possible video quality and just transcode, which might not be optimal. So using potential solutions that are closer to the client itself have been analyzed, and we actually have parallel work on using CDNs to deliver data. But I would say that both approaches are valid, and definitely the one that uses caches along the path can help improve the quality. There are two problems. First, that we're going back to the thing where the video client has to select. So you're not really using the network resources that we were hoping for, where you actually can query for. I mean, you can have a better view of what's going on. And the second part is that this solution can actually work in both cases. So say, for example, you have ways of caching content closer to the client. Now, you can just expect to cache the best quality that you ever received for that specific piece of video, and have it closer to the client. Using the name object abstraction, we go to retrieve the closest one, right? Because that's where the networking comes into play. Now, if that video exceeds the type of rate that the client could support, you can actually still invoke the local transcoding setup, right? So they are actually they can be merged together. So both approaches are valid. Maybe a combination of the two is even better. That's what I hope.
I guess people here that understand that better, but my casual understanding is that you usually have different videos at different rates cached on these content servers, and then you just select one of the streams.
That's usually how it works.
Yeah. So is there still a big benefit of transcoding if you have these videos cached?
Well,
there is a saving in terms of space, right? Saving multiple resolutions occupies a different amount of memory.
So
saving a single one,
the computing cost is cheaper than the storage cost. Is that the argument?
That's a nice trade-off that probably should be analyzed. Like, where do you want to have a trade-off there? Like, based on the amount of data that you store or the amount of computing resources. But I don't have an answer for that. We didn't test.
So what about on the other side, if I don't like your transcoder? Two transcoders with the same quality factor don't necessarily give the same result. I mean, that's generally known.
That is true.
Yep.
But
And if I'm the end user and I wanted the left implementation and not the right implementation because, I don't know, for some reason, how can I tell the network, transcode this way for me, not that way?
So this is actually part of the work in the sense that there is one aspect that I didn't cover, is that how I deploy this in network computing. And I think that it's a reverse approach. Here it's not really the client that says who wants a given transcoder, but it's more the service, in this case the video server, that sets up a request on the edge network to say, okay, I want this computing service to be allocated for me. So the clients can't really choose much. If you watch Netflix today, you won't say, I want this, I want that. You just get whatever Netflix gives you back, right? But Netflix definitely wants to save as much as possible in terms of what it's using in cost. And we could argue if they have to pay the edge network or not, but I guess that's a different discussion. But in general, yes. Is the content server, the one that is transmitting the video, is in charge of deciding whether this service should be invoked or not, right? And that's an agreement between them and the edge network. It's not something that always comes at whatever. I mean, that should happen in any case.
So you're
extension header allows you to specify
Exactly.
different kinds of coding.
So this is the way we implement it. As I say, we give two options. And by the way, networks are doing that. T-Mobile is cutting your data rate even if you don't want to.
I know.
It's your bit rate. So networks are doing it. So you can't technically stop them from doing those type of things. But the idea is that the service that is deploying this can provide the type of information. So what we were doing in the experiment, and I'll talk maybe a bit more at the end, was giving throughout some arguments A, the type of transcoding that was requested in case, and B, referring to the fact that they wanted the service to be involved if necessary. So they had the freedom to select that.
So, Francesco, to answer Wade's question in terms of transcoding quality, right? One place where this could be very useful is that content providers will, so you have multiple bit rates, so they will do 1080p 6 megabit per second till say 480, not 480, even lower, 240p at say 750 kilobit per second, right? So there are two things that are happening here. One of them is the latency on the path, which is why you want to push the anything that you do, additional support that the network provides closer to the user, because especially when the user is mobile, the path latency can get in the way in terms of fluctuations and responding quick enough. So in that case, anything closer in terms of either the edge cache or this kind of an approach will help. Okay. Now the second thing is that in terms of quality, as far as the client is concerned, if it is only, so there are two cases to take. One of them is that there is no in-network support, no edge cache or otherwise, in which case the client will only get 750 kilobit per second. He might have a 500 kilobit per second link, and then 750 is going to be way too much for that. So where the in-network support comes in is that it can provide lower resolution or lower bitrate cached content in addition to what is already available, right? So now, in terms of a business point of view as to why they should do it, that's a separate argument. But from a technology point of view, will that help the customer? For sure. The user will, when he has a 500 kilobit per second link, he will get a 500 or a 480 or a 450 kilobit per second stream, which will be supported and which will be, non-stop as opposed to having jerky movement. Okay. That still leaves open the question in terms of whether you should use an edge cache and involve the client, or you should use this approach. That's something for you to think about, and I don't know the answer to that.
And I'm pretty sure that there is a good amount of trade-off there.
Right. Now the second question for you from here is that if you say that your in-network transcoder is going to detect the client's, it's going to do that without the client being involved, right? Isn't there, so how are you going to do that? Are you going to query the base station? Or
Exactly, that's exactly what we were doing, querying the base station for quality.
Okay. You're querying the base station saying what is it, what is the trigger when you query the base station? When do you do it?
That's part of the...
Because only the client knows how bad his traffic is, right? You need some kind of client involvement? Because only the client knows that the video is degrading, for example.
It wasn't really invoking in terms of video quality, it was more about connection quality.
But there's another point there, right? The client only has a limited ability to measure the network conditions, whereas something within the network has a wider scale of view. So the ability to predict network failures or predict some bandwidth loss is not really something the client has the ability to touch.
The client does it today.
So the client
The
is...
client does it today.
Well,
What
yeah,
the
but
client
the
does
client
is-
has less view of the network.
Sure, but it only needs to view its own link. And that's the beauty of it, right? It's distributed. There's not like a centralized, you don't have to worry about scale and compute cost and all that stuff. The client, it's very simple and elegant in that sense, where the client measures its link, which it cares about.
But
And
the
it
client-
knows when it needs to care about it.
The client really measures it's just an application overview
Right.
of what the hell is happening.
Exactly,
And
just a TCP.
It doesn't have,
bandwidth.
it's just, okay, the last few chunks I received them in a certain amount of
Right.
time. I'm assuming that will be the quality that I'll get.
Exactly, right.
So you can improve, and I've done some work on that, but it's not part of the thesis. I've done during an internship,
Right.
where you actually can say, okay, you can do a bit more looking at, if you look forward, if you look at the future, you
Right.
can do more to predict what
Right.
the quality is.
Sure, okay. There's one more point before I let you proceed from here. So this is a real world problem that that we saw, where basically you have a content provider, you have a network operator, and then you have clients. Okay. the content provider is using HTTP in today's world. Initially, like this was 2015, they're using HTTP. The network operator wants to intercept that traffic, and depending upon traffic conditions, send less bandwidth when it is necessary and send more. In other words, they wanted to intercept a YouTube video or something like that and transcode it on the fly and deliver from their network cache. Now this is fine when you have HTTP, but when you have HTTPS, it's the classic man-in-the-middle attack. So the question for you is that, from your architectural perspective, is it possible to do this in a transparent manner where the client doesn't really care? He's just like going to youtube.com, right? But somehow there's a magic that happens between the network operator and the content provider, where magically, when things change at a faster clip in the mobile network, right, for that particular client or for a set of clients, automatically the in-network transcoder versions show up at the client without having, without requiring any business relationship between the content provider and the network operator.
That's a nice point, but there is one fundamental shift in this type of architecture with the scenario you're talking about. In today's video, you're really talking about a point-to-point connection.
Yes.
So the way you secure this channel
Yes.
is by basically encrypting everything, so you don't see anything.
Yes.
Here you're querying for named content.
Right.
So you already know that what you're retrieving. Now, obviously you might talk about whether you want you to, like, the network know that you're retrieving the specific content.
No, even in the HTTPS case, you know the URL is in the clear. I mean, whatever you're querying, that URL, and you and I can read, and so can the network in the middle. So the named object kind of is similar, right?
But now that means that if you actually are using that to encrypt, you're still invoking the service as something that you deploy there and say, okay, I want you to. So you might have ways to share a key with that service and say, okay, if you're encrypting my content.
Yes.
And it's a lot more secure because you know exactly who's the source, and you have, like, CDNs today can't do that.
Yes.
They have to have all the content, they can encrypt it.
Exactly.
So you have ways here through that.
So that's what I'm asking. You have ways here to do that without requiring that?
Yeah, for the reason that basically you can share the name are public keys, and you can share the security properties to actually to different locations. Well, you can do that in a setup like in CDNs today, because that's really just an end-to-end relationship between you and the content provider.
Right.
Okay, and this concludes the second part of the talk. I'll speed up here a bit. So now, after we have defined these services, one question came up. Okay, we have these new services within the network. We have this API at the end clients. But how this relationship affects the way that transfer services should operate? Because obviously, the classical transfer services that were designed in the past, like TCP, were built to support the end-to-end host-to-host communication. While now we're talking about, in all the different name architectures, about different paradigms of communication, like getting a content through Anycast, where you might not have an end-to-end path, or sending to a group of devices, and more. How can we improve transport protocols to support this? So first we set a few requirements of what we believe that should be supported. One was the ability of fragment and reconstruct end-to-end transfer of files, and this should be done transparently for the client. So the application requests a content, it gets the content. It doesn't have to worry about that, and it doesn't have to worry about other issues. Second, provide ways to optimize the end-to-end path in different type of link conditions. Wireless is an example where it's widely known that if you split the delivery path into a hop-by-hop reliability manner and only handle end-to-end recovery through feedback, this can improve conditions when in the scenarios where you have different type of links across a data path. Third, exploit the fact that we can better support mobility with names to recover from mobility events and disconnections by the use of transport proxies. Then having a different congestion control mechanisms and support multicast delivery as a baseline. So we came up with what we call MFTP, which is a set of technology enablers that can support these different requirements. And this provides an overview. So there are 4 core key designs in MFTP. First, it supports efficient content-based transfer. So as I was saying, you want to avoid headline of blocking. You don't want to have different contents to be dependent on how it's being delivered, like how the first one that you started retrieving is being delivered. So it has to support content delivery. Second, it can recover from sporadic failures in the network by using end-to-end feedback. And it can support mobility events by using transport proxies that can query the name resolution service for the new location of a client and deliver that. And finally, it supports a hybrid unicast multicast reliability mechanism. This means that basically if you have a multicast group and you're delivering that to this multicast group, if only one client didn't receive a specific packet, a specific piece of data, it can, through a unicast channel, request it back to recover from this. Going a bit more into the details of a couple of aspects of this design, as I was saying, it's intended to support large files delivery, and it's very important to define this loose relationship across different files and have strict reordering only within the confines of the given file that is being transferred, and provide in-order delivery for these data chunks that belong to the same file. This can allow for avoiding head-of-line blocking and out-of-order receive. Second, this provides an example of how transfer proxies can implement and support disconnections. And this is done basically by using a notification system that tells the sender that the receiver was not available at the time for delivery and that data chunks will be stored. Once the client reconnects, it sends to the other side of the communication a notification saying I didn't receive these pieces of content, and instead of having to retransmit everything from the end to end, the sender can notify the transport proxy to re-establish restart transmitting the data that was stored. So using Orbit and this experimental setup, we try to understand how our design can improve performance and quality. And we look at different scenarios. In particular here, we focus on content retrieval and web content retrieval, which have slightly different patterns in the sense that content retrieval was aimed at retrieving very large pieces of data. In this particular case, I think we were talking about 20 megabytes content. And we were looking at how these connections could affect the retrieval time and compare it with TCP. So basically we were setting up a random time between 0 and 10 to start retrieving the content. Then at 10 seconds there was a disconnection period, and after a random time the client will reconnect and complete the retrieval. And we saw that TCP, due to its exponential increase in timeouts, takes a lot more time to recover from this type of failures, increasing the response time, the amount of time to retrieve the content. The other aspect was in web case scenarios, which are different in the sense that you're retrieving a lot of different contents in a row, of different sizes, of widely different sizes, and they can be very small. And we analyzed the page load time under different conditions, and what's very interesting to see there, this is like a single, these are different pages. It's interesting to see how, first of all, MobilityFirst, the MFTP is a lot more stable. The variability of the retrieval time is a lot lower. And that's because of there are no heavy setups. So in TCP it requires the handshake, the full handshake to start transmitting, while we can rely on the reliability available within the network. And any packet error or loss is recovered locally, which reduces the impact of end-to-end retransmissions. So this was the part where we defined a transport protocol to support the services that we had implemented. But these services were all the base services that we defined as core abstractions, we defined as something that we wanted to support. But then we start asking ourselves, what if we want to do more? What if we want to support more advanced services that might have a lot stricter requirements and might need more from the network? So one technology and one technique that has been widely used in the technology community to support advanced services is network virtualization. But network virtualization has gained a lot of traction in localized domains, for example, cloud networks, because it provides flexibility, it provides ways of reliably connect resources, but there are not so many ways to deploy the same type of services in larger domains, or better in inter-domain scenarios, because there is a lack of ways of actually coordinating the resources within these domains and to share service-specific requirements. So we exploited the named object abstraction to define a more clean and simple way to introduce virtual networks in inter-domain networks. And on top of that, we designed what we call application-specific routing that can enable routing decisions to be made within the network fabric to enhance services. And I'll talk about that. So one important thing to capture here is that we now don't have any more a virtualized layer on top of the physical infrastructure, but we have 3 layers of abstractions. First, the physical layer, then the name of the resources on top, and then the virtual names on top. And this is very important, and I'll come back to that. I just wanted you to focus quickly on that. So what are the core designs of NoVN, of our virtual network framework? Well, first of all, we use the GNRS service plane to have a clean way for defining a virtual network and manage its resources. And we do so by overloading the definition of what a virtual network is into the name resolution service. So first of all, we identify a virtual network as a unique object that has a name, and that name is placed into the name resolution service. The locators are actually other names, and those are the names of the resources that are participating in the virtual network. So you have a list of all these participating resources. If you want to get their location, where these resources reside, you can recursively iterate from the virtual router network name to the router name, which is also the second layer of abstraction here. So we have a VR1 that is mapped to R1. Finally, the router name is mapped to its network address. This is very important for managing the network, because it allows for a better abstraction of what the virtual network layer is on top of the infrastructure itself. And how can we deploy this? Well, it's somewhat similar to what we did with Multicast, with the difference that we can uniquely identify and provide full information for each router belonging to the virtual network to reveal the local view of what the virtual network is, by first identifying that a packet is part of a given virtual network traffic, by placing the ID of that virtual network in the network header, and then use names of the virtual routers to tunnel data through the network. there are a set of benefits for doing this. So first of all, this provides a better virtualization abstraction. What I mean with this, if we look at the IP world, migrating one virtual router from one location to another is rather complex. That's because usually you have tunnels that are established from a given address to another address. If you want to move those resources to another location, you need a new address to be established, to be propagated across the resources. Is rather complex, and that's due to the way IP resources are defined. In our case, we only need to modify the layer at which the change is happening. So for example, if virtual router 2 is moving from one location to another, I really just need to provide a new mapping of that location at the main layer, so where the new router will be. And resources can simply dynamically re-retrieve these, and actually ongoing traffic will be forwarded without any loss. Second, it provides a clean way to separate global problems, global tasks, and local problems. That's because, well, if you need to coordinate across domains in an IP war, you need to communicate everywhere what are the resources involved, establish tunnels, and deploy them. In this case, a local service can decide where to better place the virtualized resources, and only communicate to the higher layers, to the higher coordinators, the names that are belonging there. So you don't really need to do any work in terms of sharing your physical infrastructure, which simplifies the coordination across domains. Second, being able to forward based on a single virtual network identifier and not having to all the time have to map virtualized resources to physical resources simplifies forwarding, because now you can simply do header matching and not have to worry about header fields matching and not have to worry about all the mappings. And this was proven by some basic experiments that we did with our prototype, where we saw that the overhead is basically minimal in terms of compared to the baseline MobilityFirst scenario. And finally, our design is protocol independent, which means that it can support technically any routing protocol in the virtual network layer, because there's no real requirement for what in the relationship with the lower layers. But at the beginning, I talked about that we wanted to support more performance-oriented routing protocols. How can we do that? So we do that by exploiting one nice abstraction that comes into play from named objects. So we can map a name, in this case y, to a set of resources, which define a service. So in this case, we can define a way to say, okay, I want to send a given piece of data to the best possible location of that service. So we have a named object that represents this service. And if these service endpoints can share snippets of data, snippets of information about their application state to the participating resources, you actually have a clean way to take more informed decisions. So looking at an example in this case, let's say that service Y is a cloud network that is replicated on multiple locations, where a service is replicated on multiple locations. If each one of these locations actually share the load, the amount of current processing load that is experiencing, virtual routers can actually decide based on simple threshold-based, in this case, otherwise more complex scenarios, whether a specific data request should be forwarded to the closest location, or maybe it should be delivered to a location that is more far but has better availability in terms of resources. So we actually implemented a use case for this scenario in conjunction with our virtual network routing layer to deploy real-time cyber-physical applications using distributed cloud environments. So the Japanese group provided virtualized resources at the edge network. I won't go too much into the detail there because it's late, but the idea was to try to optimize data delivery to cloud locations using our virtual network infrastructure. And we actually deployed these on orbit. The base scenario that we used was having multiple locations, multiple cloud locations, and generated traffic at the endpoints where clients will generate cloud requests in varying network conditions. We had also traffic generator to generate noise traffic. And we wanted to see whether we could reduce the response time under 100 milliseconds, which is the threshold that we define as the time for which a cyber physical system should have a response from a cloud location. And we actually saw a definite improvement where up to 94% of the requests were actually satisfying the 100 milliseconds requirements compared to the 46% of the baseline scenario. So this concludes the part of the talk where we focus on trying to use virtual networks to deploy more advanced service support in the network. So one important aspect, as I talked about at the very beginning of this talk, was how much important was throughout this entire thesis, try to understand how all these different components could map together into a single end-to-end service realization. And we did so by using a developed prototype, which I spent a lot of time working on. And this prototype had 4 core guidelines that I think are important. First of all, we developed everything from scratch. We didn't want to be dependent on specific architectures, and in particular on the current IT infrastructure. Second, we wanted it to be as portable as possible. It should not be reliant on any software libraries that could compromise its usage on other, on specific components. Third, we wanted it to be adaptable to as many environments as possible, it being different technologies, wireless links, or different type of devices. And finally, we wanted it to provide an easy way to control experiments and collect results throughout the entire end-to-end network. So, 3 core pieces, technology pieces were developed, and in particular, I worked on a large subset of them. While the GNRS was, the name resolution service was implemented before my arrival, I've been working mostly on developing the routing technology, the software router, and the client network stack. And I'll talk a bit more in deep about them, but everything else that was built, the virtual network, the applications, all the use cases that I talked about were built on top of these 2 core components. So first, the stack design. I won't go too much into the detail of all the different components, but an important snippet comes from the fact that, well, we developed this network stack as a user-level application that injects and captures packets using PCAP. It provides ways, it exposes an API that implements the API I initially talked to applications. And it has built-in policy management for different type of traffic requests. So for example, try only use wireless resources, Wi-Fi resources, or use the best possible interface available. And it provides a clean interface abstraction that can adapt to different network conditions. Second was the router design, which implemented the hybrid name-based routing and service that was exposed by the use of the name resolution service, and implemented different type of data delivery based on the service identifier request. that I talked throughout the work. And an important aspect is that also this piece supported different type of interfaces through a simple interface class abstraction. Oh, and this was implemented on top of the click framework. So one important aspect to consider before concluding is that, well, throughout this work I talk, and actually I had questions from Kishore about this, is how can you, I mean, what if you wanting to implement everything you talk about in the current infrastructure? So it's important to somewhat reconnect to the current state of the network infrastructure and find ways to deploy our ideas in a more incremental fashion. So I identified 3 core aspects that could enable us to deploy. First, using overlay. This was exactly the aspects that I was talking, answering the question to Kishore. Use overlay on top of the IP services to implement this type of communications, and this is similar in spirit to Lisp. Second is use tag-based solutions. So think of mapping names to VLAN-based flows, for example, as by the picture. This is definitely a potential solution, but it could be limited to a single domain. And finally, obviously, with the explosion of software reliance and software-defined networks, new technologies could open for more native solutions for deploying our ideas, either by extending OpenFlow or using alternative solutions. But what's important is that all the different technologies that I develop are flexible enough, use these interface abstractions to support different scenarios, all the different scenarios. So I said how important it was to deploy an end-to-end service realization of my work, and we actually use the Gene infrastructure to do so. So we maintained over these years along a slice of resources in this infrastructure that was running our prototype components across 7 different sites spanning the US, and included both wireless and wired resources. In particular, WiMAX and Wi-Fi for the endpoints. Obviously, New Jersey identifies Orbit, and a gigabit backbone connecting the backend. So I talked before about the in-network transcoding, how we deployed it. We actually deployed it in this setup. So this map is the same representation as the one before, but we deployed the video clients here at WinLab connected through the WiMAX and the Wi-Fi interfaces, and deployed the network transcoding in the network close to the endpoints, and we run the service while the video service was running, the content server was running at Wisconsin, and we kind of started trying to get the results of trying to understand how this type of approach could impact the amount of resources that are used in the network. And for example, in the future we could look at how caching could actually differentiate in that sense. But this concludes the last part of the talk, where I talk about the end-to-end, and I'm actually trying to speed up a bit because I know that we have some time constraints, so I'll just conclude. I went through all the different stages of my work, where we talk about all the different components that I worked on and developed over the years, and all the work that has been done for trying to get to this end-to-end realization of the work. Now, there is definitely a lot of work that could have been done, that could be done in the future, continuing this. But I wanted to mention that there are a couple of potential work that maybe some other students will pick it up, which are trying to better define how this whole network could be deployed. because I presented the considerations of how it could be deployed on the current network, but this definitely requires more work in the future. So I'll skip through these because you don't want to read all the list of papers that I published, but I definitely want to stop 1 second citing all the demos that I've been working on. And just one last thing, the acknowledgements. I've been joking about the fact that I would have not acknowledged any person because I don't like those type of things, and I only would have acknowledged the coffee machine for sustaining me over these years, but that's not true. I mean, I have a lot of people to thank for, and I definitely want to start from thanking Ray for all the support he gave me. It was 4 years and it wasn't the easiest thing ever. I had my down moments and he always was there for me, supporting me as a person. And I could not be more grateful to him about that. And Ivan was always there too. One thing I could say to all my colleagues here, you can't leave WinLab without being on Skype at 3 a.m. debugging things with Ivan, otherwise you don't get a PhD from here. I would like to thank the committee for going through all this, and all my colleagues and family that is actually watching me from Italy, I guess, hopefully, and all my friends that really helped me get over these 4 years. And thanks. This concludes the talk.
So you talked about in the end about the implementation and the connection with SDN. So the implementation right now you have a click-based data plane, right? So do you think this would be a right candidate for implementing with P4? So you also get the hardware. In that case, you can also do a faster implementation.
So we did spend some time working on mapping these concepts into SDN, and we have some prototypes that actually look at that. It definitely can, and it's very important because it provides ways for directly going to more native scenarios where you don't actually need to run everything on overlay on top of IP. These would require obviously extending the protocols. I mean, OpenFlow that will not support these as of right now. But there are different proposals for SDN, one for Huawei example, that actually are able to support different headers, different network protocols from the start. So that's definitely one way to go. As a solution for a single domain, strictly using SDN will not scale. It would more be an island approach where you solve a single domain and then you need to do something else to actually solve the interdomain problem. So yeah, I see that as a potential solution. We definitely try to spend some time on that, but more work is needed. It cannot be the only way to solve all issues.
So there's a GUID is a public key type of thing. So you generate.
Yes.
Okay.
So I didn't spend much time talking about that, but the MobilityFirst architecture is based on on 3 levels of names. The one that's a more human readable name, similar to the spirit of URLs today, where that are used by name certificate systems to generate public keys, which are the unique names, the global unique names that are used in the actual network layer, in the narrow waist, and then the network address space at the bottom. So yeah, those are.
So Francesco, I think it's worth mentioning that there's now some movement in standards, and some people are talking about standardizing some name-based solutions with previous work like HIP and Lisp, and we were also asked to contribute to this IETF new committee that's been formed.
So the question I had was here, once you essentially have the same kind of issues that a PKI infrastructure would have in the naming, right? So you have central trust authority.
So there's no single trust authority nor model we can have in other.
So the idea is that the UID space is large enough that probabilistically you can have multiple certification authorities that can generate these names and do not collide. So the model is that you will have multiple of them, maybe specialized, for example, in contents or services, say defining context and so on. So it's not a central algorithm as it works today.
It's like CAs today.
Right. So, but the thing is now with all these worries about the malicious state actors and all this, there's issues about if the CIA is compromised, then you don't know who you're talking to.
Right, the CIA is going to merge with KGB.
So the question is, performance issues aside, some blockchain-like stuff where you don't have a trusted authority at all, kind of be a support for this, right? So there's all this talk about private blockchains where you don't necessarily need to rely on you still have public keys, like in Bitcoin, for example.
That's part of the model that we talked about, self-certifying nodes who can be an individual or something.
So that way you can eliminate a root of trust. So that might be a thing to look. But of course there will be performance issues because the write rate into a blockchain is very limited. I mean, the read rate can be high, but the write rate is very limited. So the other question I had is, if we talk about virtualization and stuff, so in general, when you have like pure IP-based stuff, it's very clear how you segment different. Like for example, I want this group of servers to talk to that group of servers. It's very easy to do that. You just put ACLs to do it, right? So you have define policies, and then you have ACLs implementing that. So what's the equivalent of that in the name-based architecture? If I want to implement a policy saying, I cannot access this, I guess you would have there will be an equivalent of that, right?
So yeah, in the general idea of our framework was to basically create the infrastructure that could support all these different services. So when you say, it's clear how you do it in IP, it's true, but it's not as easy. As I was talking, like the IP space, you need to do a lot of tricks to actually get these resources to coordinate. Here you have a single unifying layer, which is the name, that actually provides you an easier way to define these. And actually, maybe it's easier. It's actually exactly what I was talking about here. When you say like in IP, it's clear if you have a single domain. Yes, it's true. Like this single domain cloud scenario where you map a given type of resource, it being say a VLAN or an IP address, and you say, okay, whatever talks on the upper layer there is only nodes of each other, but the underlying network needs to support these connections. This same type of view is provided by the higher virtual layer, where the resources that are participating in there know exactly that they are talking only between them. They are actually don't need to be aware of anything that happens underneath. What that service that you were talking about will have to do is provide this part of the mapping where you map the blue layer with the red one. And you say, okay, I'm allocating that resource there, and if I have to deliver some part of data, it will actually have to traverse this part of the network. But in my believing, like this is actually a cleaner way to say, okay, these are the resources that will participate in the virtual network, because we have a clear separation of what is the virtual layer on top that belongs to that specific network and what's underneath in the infrastructure.
So he asked the question that how do you implement policies? So the GNRS actually embodies the virtual network topology fully. It doesn't require any third party to do that. So the GNRS table can capture some amount of policy, but you can have a separate service that also. Any other questions? Wait.
You made a side comment earlier on Multicast. My understanding is that was a point where multicast was implemented practically on every router, but not turned on. Have you looked at that history, and do you see the incentive structure being different for a name-based multicast solution so that it would actually be used? Yeah.
So we definitely look at this work that was done with Tracy, so we definitely look at what was there. And multicast has been, I mean, in the research community for decades, so there has been many attempts to actually get it.
Not just in the research community, right?
No, I mean, it's there, but
it is on production routers, right? Probably still is, right?
Yeah, it is there, but it's not used much.
But when you get to to the example I was making, like when you get to multiple interdomain networks, it's just not convenient to activate it because the cost of deploying and maintaining all the control overhead is impractical. But when you get to a solution where this control overhead drops down so drastically, then yeah, there might be some incentive. And the number of applications that today might benefit from these multicast services are multiple. Even if you just look at the, say, simple case of social networks. I mean, all these video streams that are generated today, those are all point-to-point, and they're very expensive. And network operators have to face all the traffic every day. If they can see that there is a benefit, and the control overhead is not big. The number of use cases where we can actually gain something from the deployment of multicast is definitely high enough for that, yeah.
If that's only a control overhead problem, why current multicast is not used?
Well, it's also a coordination issue. Like, you have to have all the participants to agree on the fact that they have to participate, and in the moment you have one that is participating, one that is not, you're already breaking whatever you were attempting at, unless you implement something on top. So yeah, definitely you need participation from parties involved. But
so I think one difference is that in MobilityFirst we designed multicast as an intrinsic basic service. Every router is multicast aware and does multicast copy and forward. So it's not, it doesn't have the same overhead. But ultimately it depends on the business model. IoT query to all BMWs in the state of New Jersey. It should be easy, right? But it's not.
Not everybody may want to permit that, right?
Well, BMW wants that, we should. And actually the reverse is true, that they have so many weird symbols popping up that you need also to have the reverse path.
On the dashboard, you mean?
Okay, so I think we are out of time, so let's thank Francesco, and we have a short committee meeting. And there are some great chocolates outside which I had for breakfast. Don't forget that. Do you have anything in your page?
Yes.
We have it become driving proposals again.
Well, so this guy who used to, Costiara, used to work with us. Now I met him, but in Bocom, program doing meeting. He's very just talk about all the big programs now there is.
Don't know what's happening next year, though.
Was the election or?
Yeah, there could be major cuts in education and research.